Yeah, today we are glad to have Dr. Bob Olsen. So he is very well known in the area of the high voltage engineering, and he has been with WSU more than, how many? More than 30 years, huh? I didn't count that.
Count that high.
So yeah, but we all know him, but just following this format that we follow, let me just real quick go through his bio. So he got his bachelor degree in electrical engineering from Rochester University in 1968, and then master and PhD degree from University of Colorado Boulder in 1970 and 1974. And he has published a lot of papers, books, especially the book that published by EPRI on high voltage system for 200 kV and above. And recently has published 2-volume book on high voltage overhead transmission line electromagnetics. He is fellow of IEEE, and he has contributed in so many standards, working group on electromagnetic impact in power system. Especially he is the past associate editor of the IEEE transaction on electromagnetic compatibility and radio science. So with that, once again, thank you for agreeing to give a talk. Yeah, floor is yours.
One of the things I did, you mentioned the book I wrote. It's a 2-volume book on high voltage transmission, but I wanted to make this book for free. And so we get that off.
Yeah, that's what they were.
It's coming off. Oh, there it is. Okay. For free. So if you have an interest in these kinds of things and you want to get this, it's out there, and I can tell you how to do that. Maybe we can send something to the students if they're interested, and you can get it for free. If you happen to like pages, you can buy it through Amazon, and I charge the lowest price they would allow me, but it has a lot of colored photographs in there about transmission lines, and therefore it's still $75, but you can get it for free. So why not do that? All right. So let me tell you a little bit about this. This is kind of some work. I mentioned John Lehman here. John did a PhD here just a couple of years ago. He's now a consultant for electric. Well, he has his own company, actually in Troy, Idaho, so not too far from here. So he and I still work together. I'm going to talk a little bit about this topic today and try to do it. I know most of you are systems type people, and I understand that. And I'm going to try to make sure that you get a few enough out of this that you can kind of understand where we're going and why we're doing what we're doing. All right, so let's start out by talking about what's happening here in the present day approach for design of transmission lines. There are a lot of iterative methods you use. You evaluate radio noise, you evaluate how much power you can get, you evaluate critical flashover. All of these things, many of these things are empirical, and it's not well quantified. And it's really fairly weakly linked to capacity. You can do a lot of testing, and there are high voltage laboratories that I've collaborated with. It's costly, limited in scope in terms of what you can do. For one thing, you're testing single phase systems, and actually the reality, you have a 3-phase system. And one of the things we have shown is that there are very good, well understood limitations to doing that kind of a thing. And then over here, you can use in-service experience. You build something and you try it and see if it works, but it takes a long time to figure out what's going on. So let me just take an analogy here. First of all, the transatlantic cable. This was done back in the 1850s, and there were cables in Europe between different countries, sometimes underseas. And of course, the gold standard was that they wanted to be able to communicate between continents. And so they planned this cable between England, or actually Ireland, and Nova Scotia. But it was going to be thousands of miles long, and there were a lot of problems with this. And let me just go to the next page here. I'll show you the cable in 1858. And one thing is not showing on here, but is that you were getting about one word every 10 minutes. And that's what, I'm not sure why it's not showing on my screen. And not only that, but the cable failed very quickly after it was made. You can see it was a small cable. Well, part of the reason for this was that they were looking at these cables as if the electricity flowed in the wires, all right, and worried about, well, what the effect of the wire was on that. Well, this is when William Thomson, who later became Lord Kelvin, came along and started analyzing these things and realized that what was going on in between the wires, in between, for example, here and here, this area here, was very important. It was in the dielectric. It was outside of the wires. And that was the origin. It was capacitance that was of interest to them. Now, he didn't have the full model yet. And later on, there were a lot of interesting debates between different people. But nevertheless, they began to realize that there's something going on, that what happens outside the wires may actually be just as important, if not more important, than what goes on inside the wires. Okay, this is, here it comes now, 1 word per 10 minutes, one word per 1 minute. These are very low data rates, really low data rates. But in those days, the alternative was to take a ship across the Atlantic Ocean. Okay, so many of you know the name Oliver Heaviside, who really is the one who gave us, I think, Maxwell's equations. He made them. If you try to read Maxwell's treatise in the original, it's very, very difficult to read. It was Heaviside that really made it readable for us and gave us Maxwell's equations in the way that they are. But he developed these telegrapher equations here, and was able to analyze this and actually came up with a way of doing it distortionlessly, which I'm not going to talk about today. Actually, Bell Laboratories actually did something with that. But here in another one of the people that was important was a fellow by the name of George Fitzgerald. And he said, according to Maxwell's view, there's a great deal more going on outside the conductor than inside it. And that's really where the electromagnetics comes in, because a lot more going on outside the conductors, and that's what we're going to talk about today. Now, some of you may have seen this have anybody ever seen this on the internet? Okay, you've seen this? Well, I was an advisor on this one. I got, he gave me a special thanks for expertise, and quotes my book and actually gives a link to it to that book. But this has now had 23 million views, and his basic idea is that energy doesn't flow in wires. I have a cameo appearance in it, and actually basically said, you're going to get, people are going to challenge you on this. And that's because some of the things he said in there were not right. Well, Derek later on did this along with one of the other advisors who was a faculty member from Caltech, and I think did a much better job on this one. But nevertheless, the idea is there that what's going on outside the wires, it may be more important than what's going on inside the wires. So in the traditional view of looking at power lines, high voltage transmission lines, you focus on power flow in the wires, or you consider the current flowing in the wires. That's where all the power is, you say. And you have electric and magnetic fields, but they're kind of a nuisance. Yeah, they're responsible for audible noise. They're responsible for radio interference. They're responsible for health effects, maybe, all right, or shocks, or a variety of other problems that you have when you co-locate transmission lines with other services like railroads or pipelines. And you say, okay, that's unavoidable, but that's not the way we're going to do it here. We're going to take what's called a waveguide view, that basically when you put wires up there, what those wires are doing is guiding electromagnetic waves. They're guiding electromagnetic waves. And what we're going to do is to use the spatial distribution. That is how they vary, how the fields vary between here and here. How do they vary? What happens to them? And we're going to see that all of these things that are important for designing these lines actually are related to how the electric field varies in between those conductors. Things like audible noise, radio noise, capacity, the surge impedance loading, electromagnetic fields, and then critical flashover as well. All these things are related, and because they're related to this, one of the things that we're going to be able to do is to show that if you change one in a certain way, of necessity, another one has to change in a different way, right? And sometimes you begin to see trade-offs more easily. Well, Transmission line design has a lot of parts to it. You have civil engineering, for example, you know, to build the towers and all that. You have transmission planning. Many of you are doing this kinds of thing. But there's a whole bunch of other things in transmission line design having to do with steady state behavior of the transmission lines, their capacity, magnetic and electric fields, audible noise, all these things, but then transients as well. Let's go back up here. Transients, switching over voltage, and that becomes very important because when you first build a line and you connect it one end at a time. And when you connect it at one end at a time, the other end is open circuited. And what we'll see is that when you turn it on at first, a surge occurs on the line. It doubles, the voltage doubles at the other end because it's an open circuit. And you have to make sure that the line will withstand that. That's where critical flashover voltage comes in. So what are we going to cover here? First of all, I want to talk a little bit about the original insight that considering the electric field distribution. What was I thinking when we started thinking about this? But then, how do you calculate this critical flashover voltage, and how is it related to this electric field? And then calculating switching surge voltages using corona, something what we'll look at later, and we'll see if you use EMTP. How many of you use EMTP? Probably a little bit. You use that, right? Well, there's certain things EMTP can't do, and one of the things that I'm going to be doing, I'm actually teaching a course at Schweitzer right now, and one of the things we do when we're going to do this is to talk about what goes on behind the screen in EMTP. All right. Well, one of the things you can't do is you can't look at distributed nonlinear effects. And that's one of the things I'll talk about today. So part A, how does the spatial distribution of electric field relate to the design parameters? Well, let's think about it this way. I want you to consider a breakdown. This is a very simple one. The simplest breakdown in a parallel plate geometry is where what you do is you have a voltage source and you have a dielectric material, often air, or maybe in the cable case, you have a dielectric material. You have a nice uniform electric field there, and you raise the voltage until something happens. What happens? You know, can you guess what happens? Give me a guess.
Our dielectric breakdown.
Breakdown, but well, doesn't something called corona happen? Turns out that in this particular case, breakdown and corona happen at the same time. So that when you have, when the electric field gets high enough in here, it causes breakdown of the air. In corona, it causes breakdown of the air only locally, all right? But because the field is uniform here all the way around, it just causes breakdown at exactly the same point that corona starts. Now, if you look at a real transmission line, that isn't what happens, right? Transmission line, if you look at these different conductors, the electric field out here is very high, right near the conductor, extremely high. We're talking about maybe 15, 20,000 volts per centimeter, right? That's how high it is, very, very high. And it causes corona, and corona occurs before breakdown occurs. In fact, when you're designing transmission lines and you get to the point where there's a little bit of corona, what you do is you say, that's where I'm going to operate the line. And you operate it in such a way that the corona effects are something you can live with. There's always going to be radio noise. And you experience that. Maybe you're too young to experience this, but if you drive your car under a power line with an AM radio on, what happens? You hear noise, right? And that's radio noise. You also, if you just walk under a power line, very high voltage, you can hear something that's audible noise. These are all corona effects. They occur because the electric field here is high enough to cause localized breakdown of the air. But it doesn't go completely across. That would be breakdown. That's flashover, and that's something we have to avoid. So, all right, so let's talk about corona onset. This is what I call the operating voltage. What you do is you calculate, this happens to be a formula for audible noise. You don't have to worry about where it came from or anything like that. But basically recognize that what they do when they design these things is they say, there is a limit on audible noise that I'm willing to live with, all right? And so I then have a maximum electric field here, which gives me that limit. It's also related to the design of the subconductors and number of subconductors, altitude and variety of distance away, that sort of thing. Doesn't matter. The point is, you live with corona, and that becomes your operating voltage. This happens to be something that was done by Bonneville Power Administration a number of years ago. All right. There are also constraints on the electric field. It satisfies in the transverse plane Laplace's equation. How many of you took that course in electromagnetics, and when you got out of that course in electromagnetics, you said, I'm glad I never have to see this again, right? You know what I'm talking about, right? You know what I'm talking about. Yeah, that's right. I taught that course many times. All right. But nevertheless, whatever it is, it has to satisfy Laplace's equation. The electric field is related to the potential, as you can see up here. All right. Also, is true that between the conductors, if you have an electric field, there is a difference in the voltage between the two conductors or the conductors and ground. And that's a constraint, because when you design a line for 500 kV, for example, that 500, that's up here. You can have different distributions of electric field, but this is given, right? That's given. So now, when you're calculating the electric field, what we're talking about, the potential, the voltage between here and here, for example, that integral along there gives you the voltage that's fixed, but it doesn't tell you anything about how high the voltage is in between or at the center or something. That's something you can change. All right, so now let's go and talk about power capacity. When you deal with power capacity in any of the transmission line books that you have that for a long transmission line where it's not limited by thermal characteristics of the wires, you say that the surge impedance loading is pretty much what you can get. And you say that's the line-to-line voltage squared divided by something called the surge impedance, right? And if you think about that surge impedance, that's one of those concepts that's going, what's that all about? Anyway, turns out that's equal to what we call the characteristic impedance of transmission lines. And I won't say much more about that right now. But look at this formula. Look at this formula. Whoops. Oh, there it is. Okay. Look at this formula. From electromagnetics, all right, this course you hated, you didn't want to do anything with anymore, you can come up with something called Poynting's theorem, right, which says that the power, some reason it's locking up on me. Anyway, the power, I'm not sure. Here we go. The power is equal to an integral over the surface area of this power line of the electric field crossed with the magnetic field, and you integrate that. But surge impedance means, if you have surge impedance loading, it means there's no reflected wave. And therefore, it is possible to say that the electric field here, the electric field and the magnetic field are related because there's no reflected wave. In fact, they're related by this. So therefore, we can say that the total power is equal to this integral of the electric field everywhere in the vicinity of the transmission line integrated over ds. And so you say, oh, that gives me some insight into how can I get more power down this transmission line? That's one of the things you're trying to do these days, right? Trying to get more power down transmission lines if you possibly can. And so what you want to do is you want to say, make the electric field down here more uniform, right? If this electric field is high everywhere, that's golden because you get more power down there. But remember what I said about uniform fields before? That if you have corona, if you have a uniform field, you start with corona, breakdown occurs, how soon after the corona starts?
At the same day.
Same time. And so you have to have a non-uniform field. It has to be non-uniform. Otherwise, you would get breakdown every time you turn the line on. We can't live with that. All right. There are also other things. I'm not going to spend much time on this, but the capacitance and inductance per unit length, you can relate them to this electric field. But remember what we're doing here. What we're doing here is saying we're going to relate all these important variables, capacitance, critical flashover, power density, whatever, to this electric field distribution between the wires. All right. So again, here's a picture again of a transmission line. You know, you have high fields here, very low power density here, right? Very high power density here. We know that if we want to get more power down this line, you make this redder over here, more red and less blue. But we know that there's a problem with that, right? We know exactly what that problem is. And so anyway, this is just kind of the way you look at this thing. So let's think about this a little bit. And this is kind of where I got started. I got started thinking about this a number of years ago when I was writing my book. And one of the things I began to think about, well, somehow this relationship between corona onset and breakdown ought to be further away. They should be further away from each other the more non-uniform the field is. And so if you look at experimental results, for example, here, experimental results, and you say, let's separate them and let's take the case for which it's a very non-uniform field up here, very non-uniform field. Then up here, very non-uniform fields, the ratio of V50, which is the flashover voltage, this is the crossover voltage, to the operating voltage is really high. That's kind of what you'd expect. Somehow you'd expect to see that if you have a very non-uniform field, you can have an operating voltage and the critical flashover voltage is going to be very high compared to the operating voltage. And that's a good thing. But the penalty is you can't get much power down that line. And you can plot all this data in this way, in terms of how much difference is there between the breakdown voltage or critical flashover and the operating voltage or the voltage at which corona occurs. So here's this is the dilemma here. This is the dilemma that you have. If you make a power line like this with small conductors like this, the fields are in here, you get low surge impedance loading, but high critical flashover voltage, right? Down here, you say, I want to get more power down this line, so I can do that by building bigger conductors, like here, all right? And this looks like this, and I get high surge impedance loading, but I get a low critical flashover voltage. And that's a problem, and that's the trade-off we're trying to look at here. And this is another way of looking at it here, and this is the blue curve is you get low surge impedance loading, but high critical flashover voltage. And that's here. The field is nice and very non-uniform between the conductors here. That's what this is the electric field between the conductors here. You get that, you say, I want to get more power. So I make the electric field more spatially uniform, looks like more like a straight line, get more power, but I get lower critical flashover voltage. Okay, so that's the fundamental of the idea here. There's a trade-off. There's trade-offs in here, but by combining them with the electric field, we can see what the relationship is between the trade-offs. And what we're going to do in the next part of it, and I'll go through parts of this kind of quickly here, we're going to do in the next part of it is to try to quantify this a little bit. There are a couple of papers that came out, IEEE transactions on different things. I'll just leave that for the moment. There have been modeling methods for doing this before, trying to model this arc. That's happening, and I'm not going to say much more about it. There's a friend of mine named Farouk Risk in Canada, did a lot of this. I don't know the other person, but Farouk is now retired from IREC and did a very nice job with some of these early models. But here's what happens. Basically, as you increase the voltage on a conductor, between conductors, you look at one conductor here, you get corona. If you go to higher voltages, you're going to get what we're called streamers out in front of here. But after these streamers, what we'll show is that basically charge is transferred from these streamers into the conductor. And once that happens, once the total charge has been about 1 microcoulomb, this charge is a stand-in for temperature. So if the temperature gets high enough on this thing, you can create what's called a leader, a plasma channel, or a leader. Still have trouble with this thing. It's getting, all right. But down here, that you can see this down here, the plasma channel is called a leader here. And then what happens is the leader grows on the right-hand side here. The leader grows, and this streamer is kind of out in front of it, and it's kind of searching for that other conductor. And if it ever gets there, boom, you've got an arc. All right, this is what the model looks like that John and I developed.
Can you use this one if you want to use that?
Oh, well, you think that'll work better?
Yeah.
Oh, maybe. Okay, let's try that.
But I'm not sure it can.
Yeah, okay, all right. So here's your leader, here's your streamer zone, here's the other conductor over here, streamer head. We'll just say a couple things about this. I don't want to get into the details, too much the details on this, because we could, what's going on here in terms of the streamer. This is the end of the streamer here. The electric field turns out to be very, very high out here. We create a lot of ionization of these molecules. The electrons flow into here, so they flow through here into the streamer stem. And as long as you get enough of them flowing in there, the stem stays hot, the arc continues, all right, as long as you get enough of them in there. All right, and so the way we can calculate that is you have the field in here, we know from measurements is about 5,000 volts per centimeter, very high electric field here. And we're creating charge in here. So what we'll do is we'll step this thing up bigger and bigger, see how much charge we get. Is it enough to cause the leader to grow? Great, it grows. If it's not, it stops. That's the basic idea, right? So this is then again, delta Q, that's the amount of charge. And basically, if it's enough, the leader begins to grow by this much, delta L by this much. Details of this thing I'm not going to worry about. And here is essentially the process of what happens here. And I'm not going to say much more about that, except for the fact that we're trying to model what's going on here. What's going on here in this breakdown process. Okay, now if you try to do this with commercial software, it's too slow, very difficult to model the system. For example, finite element software for this is very inefficient for long, thin conductors. There is a method called the charge simulation method, which is probably better in many ways, but it requires lots and lots of things. So we developed our own method, something we call the FECSM. It's what we call Fourier enhanced charge simulation method. And I'm not going to say very much about that, except for to say that what we do is we say, for these long, thin conductors, we're going to model those as a distribution of charge because it's unknown in this particular case. And we will model those using a spatial Fourier transform. We then combine things with the point charges and the charge simulation method, put it all together, and voila, we have something that's much more efficient for doing this kind of calculation because you have thousands and thousands of charges in the streamer. You have charges along the conductors. All these things affect the electric field, and it just turns out that without this method, it would have been very difficult to do. So you have non-uniform charge density on the wires. Point charges are expanded in a spatial Fourier transform. You can combine these things, and I'm not going to go into the details, but it's much faster to do this, and it enables us to model a very complex system. Okay. So this is what our model looks like. The model you can see over here this is kind of the view of it, of what it is. And we have all these charges here in the streamer zone, in the leader zone, and then also along the conductors as well. And so that's what the model does. Now, let me explain kind of how this works. You can put this all together in the model. And basically, what we're going to do is come over here and say, look, I'm going to assume a certain leader length. And that's what we're talking about here. This is what's called the leader plus the streamer length. So I'm going to start with a leader length that's 1.8 meters long. To start here. And then I'm going to build a streamer, set of streamers out here. And so going from this point to this point, what I'm doing is the leader stays the same. I'm building a little bit of a streamer here. And I'm going to ask the question, how much charge comes out of here back to here? Maybe it's not enough yet to cause the streamer stem to go on, but I have to do the next iteration first. So I do this one first, this one, and if it continues to go up, I look to see if the total amount of charge coming back here is enough to keep this leader going. When it gets to this point where there's a dotted line here, yeah, that's just enough to keep it going. And we say, aha, okay, so now what we're going to do is increase the leader here and start the process all over again. I'll show you the full process in a little bit. But this is one where, because it gets to this point, the leader grows. In this case, however, you start with a leader of 2.7 meters here, keep going up, going up, going up, going up, going up, but eventually it gets here and it never reaches that point where the leader can extend and it's extinguished, it's gone, right? So here's the case where an arc is extinguished, all right? So we start out here, this is our leader, boom, 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 we're up here, great. So we extend our leader, we go to the next iteration, boom, 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 boom here. Everything's fine, the leader keeps extending. So we go to this one here and this one here, never gets to that point. Therefore, the arc is extinguished. Right? An arc that's completed, do the same thing, keep going, keep going, keep going, keep going. And eventually what happens is that you get close enough to the other conductor that the field actually goes up and these curves start going up like this. Once it gets to this point, it's going to get to the other conductor. All right, so this is how we can distinguish between arcs that go all the way and arcs that get stuck and stop. All right. And this is, calculation of critical phase to phase, critical flashover. We use this model to do it. And so we take for example, a system like this one here, and we're interested in, for different numbers of subconductors, what the critical flashover voltage is for this system here. And we can calculate it. And in this one, what we're doing is we're calculating using our method. There was a paper that I did together with a colleague of mine at Tsinghua University in Beijing. And he helped me on this because I wasn't, at that point, didn't know much about arc models, but he did. And so it turns out that there's experimental results measured. There's these diamonds here, measurements of the critical flashover voltage. And this has to do with a measure of uniformity, Emax over Emin. So again, this is more non-uniform field. And as the field becomes more non-uniform, the critical flashover voltage goes up. And we can do a pretty good job of matching these measurements like this, right? And so we were pretty confident, pretty happy with that result. All right, now we also compared it to data, a number of other data sets. There were 15, but there isn't that much data on this actually. These are expensive to do. There's a GE, well, what used to be GE now is an EPRI lab in Pittsfield, Massachusetts. There was some work done in China, some work done in Russia, some work done in Japan. And we basically compared our experiment versus theory here. And again, you can see these are calculations that we have and the gray dots. The experiments are here. And again, you can see following this line. But one of the interesting things, in fact, let me just go back just for a second here, because I want to go back to this one here. You'll notice that this starts here at 15. This curve always goes down. If you follow it all the way to a uniformity of 1, it becomes 1. Does that make sense? It makes sense because in the uniform field, the critical flashover voltage and the operating voltage have to be the same, right? So that's one of the things why it goes down. It'll always know what it comes to at that point. All right. Now, this is the one that's most interesting. We find the most interesting, and that is we plot here versus the minimum electric field, flashover voltage, or I should flat over the operating voltage at minimum electric field. And it always seems to happen at the same minimum electric field, almost always. And so one of the ways of thinking about this, and we're looking at different ways of thinking about this a little bit better, is that if the electric field in between your conductors is below a certain threshold, it's below it, your arc will be extinguished. One way of very simply going and looking to see whether your arc will or will not go all the way across is looking at the electric field in between the conductors and making sure it's below a certain threshold. That's what this says. And it's a very interesting result that we got out of that. All right, so basically what you end up doing here is when you do tests on this, you'll have two conductors. You start with a certain voltage, all right? You get up to that voltage, nothing happens. You do another voltage, the distribution is the same, but higher electric field. And finally, when this point gets to there's some threshold, then flashover occurs. That's the idea, the fundamental, simple idea that comes out of this. All right, so here's an example. This happens to be one that John did with a 500 kV transmission line, and looking at and basically was able to come up with a table like this, which shows, number one, this has to do with surge impedance loading. So surge impedance loading is high when the conductors are spaced closely, and it's lower when you get further apart. But at the same time, over here, this says something about the this is the critical flashover voltage. When you move here to here, the flashover voltage gets higher, right? So you kind of see this trade-off in this graph. But I'm not going to spend too much time on this because we only have about 15 minutes left. And let's look at the part C here, because part C is, so now what we're seeing is, okay, I can calculate what the critical flashover voltage is, but what's the voltage there? When you turn a transmission line on, when you first energize it, and you get a voltage along the line, right? How much is that voltage? Well, this is the kind of thing that requires transients. And if you do use EMTP, you can go into EMTP and make this calculation. One problem. There is a phenomenon that we know on the transmission line called corona, which occurs and which is responsible for loss, and EMTP cannot handle that. What it can do is it can handle nonlinear phenomena at discrete places, like a surge arrestor, but it does not handle a distributed corona phenomena. That's what we're doing here and trying to resolve that problem. And you'll see here that there was a paper that came out in Energies back in 2020, not that long ago, actually, where we do it. This is the approach we use is something called the finite difference time domain. And I'm not going to go into the details of this, but Professor Schneider here is an expert in this. And if you ever need this kind of thing, go talk to him because he's one of the world experts in that area. Okay. There's something we call recursive convolution we use, and I'm just going to say simply that this is a way of doing it much more efficiently than it had done before. There's a friend of mine named Solozzi in Italy who's developed some interesting techniques for making this method more more efficient. I'm just going to say also that when you have conductor bundles, like here, for example, as you have in high voltage transmission lines, I haven't talked about why you actually have conductor bundles, but it's actually an interesting thing. It turns out that if you have conductor bundles, you can really reduce corona effects, have a significant impact on corona effects. And this is just the way we handle that. So it's not. Now, so what you do with this method basically is you predict when you energize the line, what the voltage is along the line. So this is position along the line. This is a 100-kilometer long line, and there's a whole bunch of curves in here. Why? Because when you do this, you don't know exactly what the phases of the voltages are going to be when you close the breakers. Okay, and so you do this for a variety of different cases, and this is done for hundreds of cases using this method because the method is relatively efficient to do that. And then this is just a little bit cleaner picture of it, but it basically says, here's what it says. It says, if you do this without considering corona, this is the absolute maximum of the voltage along there that you can get. If you do this with corona loss, what happens is that the voltage is not as high as it would be, right? So this actually is to your benefit. It's one benefit from corona. It actually reduces surge voltages on the line. So if you use the MTP to do this, you're actually doing a very conservative calculation. You're getting this number, not this number, right? And this is the 98th percentile. You can kind of see the difference on that. So basically what we can calculate is, and use distributed corona here, you can calculate what the voltage is, surge voltage is along the line. Now, this is one we did because one of the things that people do, and you find that there are papers, I've been reviewing a couple lately, of papers that are coming out using EMTP to try to do this. But normally what happens is you put in just a few places where you actually measure the voltage and a few places where you can have nonlinear elements which simulate to a certain extent this corona. But if you do that, you miss something. You can miss something. You can miss locations where the voltage may actually be quite high. And in fact, it may be your critical flashover voltage at some different point along the line. All right, so let's talk about some conclusions, and we'll have a chance to talk about a few thoughts. So basically, what we're saying is that when you design these high voltage lines, instead of doing this, all of which appear to be independent things, it turns out that most of these design parameters are actually related to the electric field between the conductors. And so that gives you some insight into understanding trade-offs between different things that you can use as you try to do what everybody is trying to do now, and that is to increase power flow on transmission lines, on long transmission lines. And then we developed the line model for calculating critical flashover voltage. And again, the fundamental idea is that maybe there is this place where there's this minimum electric field between the conductors. And if that gets high enough, the arc will go through, otherwise it won't. And that's what we're trying to refine at this point. And then also we have a new model for predicting corona attenuation. If the voltage surges has been developed enough, and it has enough resolution not to miss overvoltage peaks. And there we are. So this work was supported when John was here. We had support from PSERC. Some of you are on PSERC money, I think. Is that right? You know what that is. And American Electric Power was involved in it, and Power Engineers, in addition to WSU as well. So any questions you have?
Yeah, Christopher, thank you. So it was very interesting and engaging presentation.
Yeah, and if you have any other questions about it, I'm actually quite active these days. I'm mostly working from home, but I can be here in 5 minutes. I'm always happy to meet with students. If you have questions related to anything like this, happy to do that, and I can help you out there. I used to have a course here, And I guess Monish is going to actually do it
Yeah, what I heard.
for the professional science masters in applying electromagnetics to high voltage transmission. And it's EE 526. It's on the book still. And we are going to offer it. One of our recent PhDs, Monish Mukherjee, is now down at PNNL, took the class the last time I taught it, and has actually helped me as a TA when I offered it for the professional science masters, and we'll be teaching it in the spring. So I don't know if it can be made available to you, but I've often offered to people, if there was enough interest that people really wanted to do something like this, maybe we can find a way of reviving it here, but I don't know how that would be at this point. Anyway, so that's the seminar. That's what I had to say. If you have any questions right now, that's fine. If not, we'll break up, and if you have questions individually, I'll be happy to answer.
But maybe check the people online. Do you have any question? If you have question, please unmute yourself and ask.
Yeah, I don't.
If not, yeah. So okay, you guys.
Anything?
You were physics guy.
No,
I was hoping you can.
yeah,
have
no,
it.
no, definitely. So I guess just to make sure I'm understanding, basically the issue being that in the initial designs, the voltages at starting are being overestimated because the coronas are not being considered.
Exactly.
Is the main.
Exactly. That's right. That's right. So you're being conservative.
Mhm. And so you talked at the beginning about the experiments that have been run on or lack thereof.
Yeah.
If you could say run any experiment to sort of further nail this down or conclude it,
Yeah.
what would you like to look into on an experimental level?
Well, one of the things we've talked about doing, for example, is to say, are there some other parameters? In other words, maybe it's not just the field in the beginning, but how wide it is, for example, right? How long it is trying to get through there. Because if you have a very gentle curve, it may be that it's not just the fact that the electric field here is minimum, but it's minimum over a certain distance, right? And so we may be able to refine this. If we could get that into a very nice vertical straight line, then you have a very simple criteria for whether you're going to have critical flashover voltage or not, because the electric field that you use is the electric field before anything happens. The electric field before any sort of flashover begins to happen or whatever. It's that electric field that you calculate very simply using Laplace's equation. Very simple. That's what we'd like to do.
Hmm. So you would expect sort of the topology of the electric field obviously would change while the corona.
Oh yeah, and that's in the model that we actually do the calculation. All that is changing, right? Because the charge distribution along the wires is changing. There's a charge distribution along the leader and all this kind of stuff. And so the electric field between the streamer and that other conductor is quite different than it was in the beginning. Absolutely. But when we refer it back to this minimum field, we're referring to the minimum field that existed before anything happened. And that's a very simple one to calculate. That's a two-dimensional problem.
Sure.
He got his, but you know that he got his bachelor in physics.
Oh, is that right?
That's
Okay.
what I was saying.
That's good. I'm half a physicist. I took, I actually was very fortunate that I took several physics courses and, several courses from this one guy who, in fact, I took quantum mechanics from him, but later got a Nobel Prize at Colorado. He's now at, he's still active. He's at University of California, Santa Barbara, but he taught quantum mechanics in the double E department, which was a lot of fun. And then he recruited me to go into a seminar that he was organizing on superconductivity. And I presented a seminar, but I can't remember anything about it. In fact, I haven't really used my quantum mechanics since that time, but it's nice to think about.
Sure.
All right, that's great. If you want to stick around, sorry.
Yeah. Thank you, Professor Olsen, for
Yeah.
putting this together for us who
Yeah.
might not be super familiar with this. So So I just want to, like clarify one thing. So, for example, the graphs you showed, I mean, the plots you showed with the leader and the streamer, like
Yeah.
how below some critical threshold, like they can never cross.
Correct.
So, does that mean, like, I just want to clarify, like, if Corona, like that flash does not happen, so we can say that there is no loss which happened due to Corona?
Okay. Generally speaking, you're well below the critical flashover voltage. Even when, for example, let's suppose you have a surge, you basically energize a transmission line for the first time. You just built a brand new transmission line, and you want to make sure hopefully you've designed this so that when the voltage doubles at the end, because at an open circuit, the voltage doubles on a transmission line. When that doubles, you want to make sure it would be embarrassing if you turned the transmission line on that you built for millions and millions of dollars, and then it flashover happened. All right. So normally, even when you have these very high surges on there, we do not get leaders and streamers and all that sort of thing. It's only when you get very close to this flashover kind of thing. But anytime you have corona, you have loss. Anytime you have corona, you have loss. And because of the fact that the voltages during surges are much higher than the operating voltage, the electric field is much higher, you're going to get significant amount of corona. And probably the best way, I don't know, let me just go back to here just for a second. It won't take much time to do this. Go back here. Okay. You might have basically this situation here, right? This kind of situation. All this causes loss, all continuously along the line. And that's what causes your surge of voltage to actually attenuate due to the corona. Loss.
Thank you for explaining. So as you said that like something like EFTP, PSCAD, cannot model this.
Right.
But then can you just maybe dumb it down for me? Like how did you possibly model that in your simulation?
The best I can tell you, and I think I won't do it here, is this. That's just here we go. Okay, here it is. I mean, this is basically the finite difference time domain program. And what you can do is you build into this thing a model for a time varying capacitance. You build into this model time varying capacitance, which is related to the parameters, the corona parameters, is the way you build it in. Right. And this is all I'm going to say at this point.
Yeah. No, thank you.
I'd say read the paper. I don't want to, otherwise. Or I'd help you work through it.
Yeah.
Right. Okay.
Thank you so much.
Anything else? Oh, no. Yeah.
So it's been a long time that I've done electromagnetics.
Yeah.
But because you're saying that anytime you want to do an actual simulation with electromagnetics, it's just too much computation, right? Like it is a lot to deal with. So people are trying to use physics-informed machine learning, and then there is operator learning to make those processes easy. Do you think industry is moving in that direction for using, because it's a good use case because we know physics so well, like the differential equations for this system so well. With the literature out there going physics-informed machine learning is just taking off.
Sure, it is.
So what do you think? What is your?
It's a really good question about AI and this thing. And one of the things I thought about is that once you have a model like this, you may be able to use it to help you understand what parameters are the most useful. All right. I think that's something you could possibly do with it. I haven't thought about it because I don't know much about machine learning. I remember from 30 years ago, looking into neural networks when I was with EPRI, for example, for a year. And I think it's a similar sort of thing, but I really haven't kept up on it at all. But I do think that there would be some places in here. I'm not sure that you can use it to replace all computations because it's all built on learning from previous models, right? And if your models that it learns from are not good, then I think you have the old computer garbage in, garbage out problem.
Right. Yeah. These ones are better if like done well. That there is like
Yeah.
other part to it. But on the same note, is there any plan to introduce electromagnetics for like power program here for graduate students apart from
Well,
masters?
I had this, this 526 class, which I used to teach here. And I think it would be possible to get it taught again. Whether, you know, for example, John could teach that course easily because he did all this work. You know, in principle, I could, but right now I'm teaching a course at Schweitzer.
Mhm.
So I'm kind of up to here. I'm officially retired, but my people who know me best wonder if it's really true.
He's
that I
not
am. So-
retired.
Oh, yeah. Okay. Yeah. So I'm always happy to talk to students. Yeah, absolutely. Yeah.
When you were going at the model that you developed, there was one angle, 60-degree angle between the ladder and the universe.
There's a what?
There's a 60-degree angle that you showed in one of the pictures.
Oh,
So is that something occurs in nature or when you modeled it in mathematics?
you mean this
that
is the kind of
60-degree
thing you're talking about, right? This?
Yeah,
Yes.
this. I mean, I would imagine this depends on
Local
on the
conditions.
atmosphere.
Yeah. You know, this is what you actually see when you actually take a photograph of it. But we model it as a straight line,
Oh.
basically, because I don't know the local conditions that cause this thing to be kind of zigzaggy like that.
Or the
But
local
we
conditions.
model it as a straight line.
And then the 60-degree, how did you get it?
This is known from measurements. This is the 60-degree thing. That's known from measurements. And so we actually use that in the model. And it's one of these, there are a few parameters in the model that you have to use from measurements. One of them is the electric field inside here, which has been measured to be about 5 kV per centimeter. One is this angle as well, all right? And that comes from, and then there is this also, this minimum charge here that you have, and that's something that's been measured. And not by me, but some very good plasma physicists who've made measurements of that. Those are the things. One of the things that we've done is in comparison with other models that have been used in the past, we have fewer parameters, to fewer measured parameters in our model. But there still are. There's some degree to which it is still empirical. Yes.
This is kind of like I guess, larger level question, but since, there's like a lot of talk of like, inverter-based resources coming onto the network, and then that's going to require so much transmission build out.
Yes.
Do you see this work significantly impacting transmission line design within that time period that is being discussed, or do you?
I hope so. For long transmission lines, yes. For long transmission lines. Shorter ones where that's thermal limitations on the shorter transmission lines, there are other things that people are using. I mean, people are, when they're thermally related, they're doing a lot of, what's the word I'm looking for? DLT. It's basically they're measuring weather parameters. There's a word for it. I can't remember what it is right now. It's just, I'm blanking on it. Where basically you set ratings on the lines, dynamic line rating. That's one of the things that's being used a lot based on weather variables. Another one that's being used is people are coming up with alternative conductors, right? And you may have read about this for these lines. And some of these alternative conductors can operate at higher temperatures, okay, than the lines that we have today. Today, you normally operate around, I think they operate often around 120 degrees centigrade, something like that. But some of these will go up to 200. Because of that, you can have higher capacities, but maybe also higher loss associated with it. And so again, there's a trade-off on that. So yeah, this whole area of maximizing power transfer, this is one. There's a woman at University of Texas, Dallas named Mona Gassemi, who's actually working a lot of these things right now, and is doing some interesting work in what we call high surge impedance transmission lines. It's, after 2 o'clock.
Yeah,
I don't want to
okay,
hold you. up
thank
to
you.
this, but,
Thank you very much.
either.
Thanks for the
Oh,
presentation.
you're welcome.
I have just one very basic question.
Yeah.
Which is, are we only concerned about the electric field, or do we also try to model the magnetic?
Well,
field?
we can model the magnetic field.
Is it something that is usually done when designing transmission lines? or do we only-
Yes, but mostly right now, I'd say the magnetic field, I've done, back in the 1990s, people concerned about the magnetic field because of potential health effects. And I was very involved in court cases on that, whatever. I think it's kind of mostly gone away right now. But nevertheless, there are regulations on magnetic fields. To my knowledge, no one has related the magnetic fields to these phenomena. It's much more natural to look at the electric field, and because it tears electrons apart from molecules. And so, but we can easily calculate the magnetic field, yes. And I've done that too many times, more times than I want to think about.
Okay.
Magnetic field is a funny thing because it's electric field, because it's voltage, it's related to the voltage of the line, it's fairly fixed in time. Whereas the magnetic field changes all over the place because the current's always changing, the load. And so that's one of the issues that's interesting and different about the magnetic field. All right. All right.
Hey, darling,